Now I'll be deriving second equation of motion by calculus method. Let's start with the derivation of S equals to ut plus half at squared. We very well know the definition of velocity is change in displacement on change in time. I told you D stands over here for derivative. It signifies very small changes. So velocity is change in displacement on change in time. Cross multiplied gives us ds equals v dot dt. Now on integrating, that means adding, since I told you that we need to add up only those variables which has been taken into very small parts. Since displacement over here has been broken into very small part, this is derivative of displacement, so we need to add up and put the limits for displacement over here. So we need to integrate displacement from 0, that's the starting position, to S, which is the final position. Substituting V as u plus at, which we already derived in part first. This ds integrated gives us S, putting limits 0 to S. This u, which is a constant, is kept outside. Now we get dt, integration of dt is t, which is from 0 to t, limits applied. This a remains as such. This is t dt, when integrated gives us t square on 2. The formula has already been explained in part first. On simplifying and substituting the limits, this is upper limit minus lower limit. Same goes for this, same goes over here. Simplifying, we get S equals to ut plus half at squared, which is the next equation of motion. Coming to the third and final equation of motion, which is v squared is equal to u squared plus 2as. Acceleration, students, we very well know is change in velocity upon change in time. Multiplying both sides by change in displacement, numerator as well as denominator doesn't make any change. Now students, this change in displacement on change in time becomes velocity. This dv remains as such, this ds remains as such. Cross multiplying ds over here, keeping v dv over here, we apply the integration. Since this has been broken, displacement has been broken, so we apply limits for displacement. Over here, velocity has been broken. ADS gives us VDV. Applying integration sign over here, limits 0 to S. Over here, we need to put the limits for velocity. Velocity initial is taken as u, final taken as v, so limits for velocity will be u and v. A is a constant, remains as such, integration of ds is S. Putting limits, over here this is v dv. Applying the formula for integration, it becomes v squared upon 2. The formula, as I told you, has already been explained in part 1. Putting limits u to v. Applying limits, upper limit minus lower limit. This 2 is taken outside. Putting v in place of v, then subtracting and putting u in place of v gives us v square minus u square. Cross multiplying and simplifying gives us v square is equal to u square plus 2as. This derives us the third equation of motion. Deriving again these three equations by analytical method. Students, now I'll be deriving again equations of motion by analytical method or graphical method. For this, I have made a graph. As you see, this is a velocity time graph. Velocity I have taken on y-axis, time on x-axis. This is a line which denotes uniform acceleration over here. Now, this is initial velocity u, final velocity is v. Time elapsed is taken on x-axis, which I have taken as t. Please remember, slope of a velocity time graph where time is taken on x-axis gives us acceleration. That means slope, the formula you must have learnt in class 10th maths, slope of a graph is given is change in y-axis on change in x-axis. The slope gives us acceleration. So slope is written as acceleration over here. Change in y-axis, as you can see, is v final minus u initial. Change in x-axis, as you can see, is t minus 0, which I have written as t. So A becomes V minus U on T. On cross multiplying and simplifying, we get V equals U plus AT, which is first equation of motion over here. Remember guys, area of this graph under x-axis, I'm talking about the area which falls under time. This area, which is actually a trapezium. Area of this velocity time graph gives us distance, not displacement. Please remember students. Area of velocity time graph gives us distance. This particular shape is of trapezium. So I wrote area of trapezium is distance. Distance is represented by S over here. And area of trapezium, as we know, is half sum of parallel sides multiplied by perpendicular distance. As you can see, the parallel sides over here is this U and this V. These are parallel sides, and this is perpendicular distance T, which I have wrote over here, U plus V multiplied by T. We already have proved that V is U plus AT, which I wrote over here from first equation of motion. On simplifying this up, opening up the bracket and simplifying, we get S equals UT plus half AT squared, which is the next equation of motion. Third and the last equation is again proved by the same equation which I have written again. S equals to half V plus U multiplied by T. Now the only change which I did over here is I have taken T as subject of formula. T from here can be written as V minus U on A. From first equation, taking this value of T, substituting in place of T over here, V minus U on A. Cross multiplying and simplifying gives us V square equals U square plus 2AS. This is analytical or graphical method for equations of motion. Now students will be deriving the equation for distance moved in nth second. First let me explain you what is the difference between distance moved in n seconds and distance moved in nth second. If I say distance moved in 3 seconds, it actually means the total distance in the first, second and third second. But if I say distance moved in third second, it actually means we are not considering the distances in the first and second time interval. We are just interested in the third part. So over here, distance in nth second, the formula for S we already derived is UT plus half AT squared. Please remember students, this formula only should be used for finding out total distance in t seconds. This is for total distance in t seconds. But I need distance moved in nth second. So what we do, we first find out total distance for n seconds. Then we subtract from it distance moved in n minus 1 seconds. That means 1 second below it. So distance moved in n seconds, we just need to substitute n in place of t. In place of t, substitute the value of n. That's your distance moved in total n seconds. Now if I find out distance moved in n minus 1 seconds, I just need to put n minus 1 in place of t. N minus 1 in place of t, obviously inside a bracket. Now if I subtract total distance moved in n seconds, from it if I subtract distance moved in n minus 1 seconds, I'll get distance moved in nth second. Now simplifying this, I get u, and on simplifying this, I have half a in bracket n squared minus n minus 1 whole squared. On further simplifying, I get distance moved in nth second as u plus half a 2n minus 1. This is going to give us the distance moved in nth second, guys. Now, let's move to what happens if the motion is under gravity. If a body is moving against gravity or if it's falling under gravity, the only changes we need to do where a body moves under gravity, that means it falls down, we need to substitute a as plus g. I repeat, a as plus g in all three equations and s as h, because in that case distance becomes height. So the equations changes to v equals to u plus gt, v squared u squared plus 2gh, and h height as ut plus half gt squared. Now the body moves up. Remember to substitute gravity as minus g because we are moving against gravity. It's a vector quantity. Direction changes, so the sign changes. The equation changes to v equals to u minus gt, v square equals u square minus 2gh, and h equals to ut minus half gt squared. This finishes up us with this particular chapter, students. Tomorrow I'll be dealing with the numerical part of this particular chapter. Please don't forget to like and subscribe my channel so that you can get the updates at your earliest. Thank you.